Good morning, good afternoon, good evening, wherever you are or whenever you might be watching this. I am delighted to welcome you to today's session. We are joined by Dr. Khaled Mahmoud, who brings rich experience in both machine learning and computer architecture. Our goal is to take a journey starting from the simplest equation, a straight line, and step by step building our way toward the cutting edge of advanced generative AI. The today or along the way, we will connect the math, the intuition, and the system that make those advances possible. Again, welcome, Dr. Khaled, and you have the floor.
Thank you, Dr. Salem, for introducing us. And we will start by explaining the machine learning and how it works to the audience. And let's get started. So we will start by talking a little bit about learning and what is learning. Before we start, we need to mention that scientists up to this point they do not understand exactly how our brain works. They have some understanding, but they don't understand exactly how our brain learns. And most importantly, how does it store the knowledge that it learned. In fact, if we do, we would be able to create machines or computers that outsmart humans, that would even think better than humans. So we all learn from our daily experiences and our daily encounters. And from these encounters and experiences, we do build knowledge. Our brain processes these experiences and encounters, and that's the learning part, and it produces knowledge, and that's the representation part of the knowledge. Now, in this slide, we show, for example, if I pick any random person and I give him hundreds and thousands of cat images, he'll be able to easily identify a cat that he's never seen before. And that's how we learn. We learn by exposure and data. If the experiences that we are exposed to is not good, then the quality of the learning will not be good as well. So it's the same concept, garbage in, garbage out. And let's get a common example, a very famous example when we were all studying in college. Students, they do a lot discuss and between themselves about which professor I need to take the course with. Some students take course with a difficult with a very creative professor that teaches the material well. For example, calculus 2 or calculus 3 is a very complex subject, and students still learn the subject very easily because the exposure to the learning material was great. The input to their learning process was very good. So they developed very efficient knowledge, and they might not be able to forget that. So this is a nice analogy to the importance of the learning material that we are exposed to. And machine learning and computer learning is the same way. You need good learning material, we call like the learning data, in order to produce good knowledge or good machine learning models, as we will see in the next slides. Now, let's start by talking about applications of machine learning in different fields. One of them is in healthcare. Machine learning in healthcare helps save lives. Doctors, for example, they try to detect or identify cancer in many types of imaging, and machine learning can help them. For example, as a doctor, you might miss a small detail in an image, while maybe a computer might not, because it has seen so many of them and can easily identify and understand the subtleties. In hospitals, I do have friends working in hospitals, even like from large to small hospitals, and they do employ machine learning to predict the patient influx. And why do they need to predict the patient influx? To help them allocate resources. If we get too many patients and have resources, we're not going to be able to serve these patients. Uh, Another good application is if for a certain patient that spend too much time, for example, in the ICU or in the bed at the hospital, they can develop certain ailments. And machine learning helps predict if a patient will develop this type of ailment. So again, if we were able to predict that, we can be more ready for the patient and probably save his life or save him long-term suffering. Now, another common application of machine learning is in factories where for the purpose, of course, the major benefit of this before we jump into the details is we save lives and we save money and we save factories from fires and disasters. Factories they do deploy robots to their facilities, and these robots take photos, and the photos, for example, analyze it through machine learning and be able to identify leaks and gases or whatever. And a good advantage is that these robots actually can go to places that is risky for humans to go physically to and take these photos. So I've also seen this firsthand where some of the companies I work at, they employ this and they how they deploy the machine learning to the robots. Now, another common example is when you open your mail every day and it tells you that this email is a spam. Actually, coincidentally, today, just before recording this presentation, I received an email from a recruiter. He wants me to schedule an appointment for an interview for a position or for a position similar to one of the positions I applied for. The link actually points to Microsoft Teams, a site that wants me to download Microsoft Teams, and it's an executable file, not from Microsoft. So imagine, I would maybe my computer would have been hacked, and unfortunately, Yahoo Mail did not mark this as a spam or as suspicious. I suspected because of the email, the sender of the email, and it's a company that I never applied for. So I was able to hopefully not download anything from that suspicious website. And another niche application of machine learning is, for example, when you run a program, you run Microsoft Teams, for example, or when you are watching this presentation, you're running a program. This was my PhD dissertation where we built models to predict energy from runtime events, such as how memory we are consuming and how many threads we are starting. This is a little bit niche. We're not gonna go into too much details into this. And now another application is e-commerce, and this is beneficial for both the consumer and the seller. It allows the seller to make more money, and it allows the consumer to be exposed to product that he really needs, and he might be even exposed to products better than the product that he has, or he might be pointed out to something that he really needed that he didn't know he would need that product. So it's not just about selling or overselling or or just taking more money from customers. Now the infamous generative AI that we use every day, like ChatGPT, Gemini, is also built on machine learning, and this is a very famous application of machine learning and artificial intelligence. So up to this point, we have covered applications of machine learning in real life. And if you realize, we mention a lot the term machine learning model. So before we dive into the details of machine learning, it's very important to formally define what a model is. What is a model? A model is a description of a phenomenon for the purposes of control, prediction, and making decisions. So this definition, you don't have to take it literally. You could come up with better definition, but this is an okay definition to understand what a model is. So let's take an example. If you've ever watched forensic files or FBI files, there are criminal profilers that build psychological profiles that we can think of them as models. And these psychological profiles help predict the behavior of a serial killer. And why is that important? I've seen this in many of the series of the FBI files. They are actually able to catch criminals or force them confess, otherwise not possible through any of the forensic means. And actually, that saves the state, the police department, a lot of money and even save lives. And if we have the time, I might go back to this part and give a very interesting story of a serial killer that shoots random people. He leaves absolutely no evidence, not chill cases, not anything. Without that psychological profiling, he would have never been caught. So let's jump into the mathematical models. Mathematical model is basically just an equation. And the most important part of the slide is that we exactly understand the phenomenon that we are trying to describe. For example, speed equal distance over time, right? If I give you the distance, if I give you the time, you will be able to tell me the speed exactly. I mean, there is no other way around that. Moore's law as well. The number of transistors double every 2 years, or voltage. That's a mathematical model that depicts a formula. Also, for it's very good to go after this presentation and search the internet for physics works and I'm still alive. This professor holds a very heavy ball attached to a pendulum and then he let it go and that ball swings back and forth. And the movement of this ball actually is being described by a mathematical model. And if the mathematical model was not right and did not exactly describe the location of the pendulum with time, for example, his face would be crushed long back. So the most important part of this slide again is to outline that mathematical models, we know exactly the phenomenon. We understand it perfectly, 100%. Now let's jump into machine learning models, the topic of this presentation, what we've been waiting for. So machine learning model, there is a phenomena that we don't, or let's say you can imagine as a function behind this phenomena that produces some data points. And this function we never know and we never will. For example, the sales of houses. A home with 2 rooms in the same location, same zip code, can be sold for let's say 500,000. Another house with the same exact location might be sold with different price. So this is what we call here the function or the target function that we're trying to estimate. And we know this function through the data points that it produces. And machine learning model tries to build a function similar to that function. So it helps us predict what is the value. For example, if I want to buy a house with 5 rooms and 2 bathrooms and 1 floor, I can somehow, okay, this house is going to be sold for like $120,000. So here in this diagram, the number of rooms goes into the machine learning algorithms and then the actual sale price. And the machine learning algorithm give us a value. The machine learning model could be a function or whatever representation it is, and we're going to talk about that. This is an estimation of the target function that we said we never know and we never will, or we might will, I mean, but ideally we never will know. We will never know that function. So in the house sales example, there are many factors that can contribute to the price of a house. For example, the number of rooms, the number of bathrooms, the location. Some factors might not be that important. And in the machine learning, there are some techniques that can help us, such as dimensionality reduction, get rid of the factors that are not that does not influence the price of the house. So we will mention this for uh, for completeness, and if you are curious to learn about this. Now let's talk about one of the simplest forms of machine learning. Is just a simple line. That's the title of the presentation. We will go from this simple, beautiful line to the complexity of generative AI and how generative AI is built from here. So we have points and we have x-axis and the y-axis. And of course, based on the x value, we have the y value. And we're trying to predict or build something like what is the function that determines based on x, what is y. And machine learning helps us produce a line that is close to all of these points as possible. So it's just very intuitive, you know. just a line, and these dotted lines tells you the difference between your prediction and the actual value. And let's jump into another or more sophisticated uh, functions. If we have a high degree polynomials, let's say a fifth degree polynomial, you would see it would be able to fit the data even better. See it kind of goes down and then goes up, goes down, goes up, much closer to the data. Because higher degree polynomials, they have more periods of increment or increase and decrease, so they'll be able to change to match the data. And if you look at the eighth degree polynomial here, it kind of really matches the data very well. And here brings the idea of overfitting you can read about, but it's not in the scope of this presentation. But this is something that machine learning algorithms usually go through. But we don't need this still to understand how the machine learning model is built. We just focus on the very basic steps that take us to how these great generative AI models are built. Now, we talked about machine learning, and we need to understand how machine learning works. And actually, this is the purpose of the presentation. And from our point of view, machine learning is the rate of change. The most important concept in understanding how machine learning works is to understand the concept of the rate of change. If you understand it, then the rest of the concept of machine learning is going to fall like dominoes. This concept might seem very simple, but yes, it is as simple as that, and you can easily build on it until you reach generative AI and neural networks. Sun Microsystems, the old company that made the Java, used to say the computer is the network, and in the same we say machine learning is the rate of change. So let's see why is that important. So in the learning process, we propose a model that we want to represent the data or predict. As we shown in the one of the previous slides, we have a fifth degree polynomial or seventh degree polynomial, and this function will actually will make a predictions. And we have the target function that we know the data points that it produced. And our predict there is something called in machine learning very common called loss function, and this helps us quantify how well did we predict. It's the prediction minus the actual. This is just an abstract. It's not the exact equation. So I predicted the price of a house to be 1 million, and actually it was sold for 1,200,000. So it helps us quantify how well did we do in a prediction. And this loss function goes back and updates the model. And again, the model makes the predictions. There is a loss function. The loss function goes back and updates the model until we reach an acceptable performance or acceptable prediction accuracy. So in order to understand how this process works, we need to understand how to minimize this loss function. And in order to understand this concept, we need to understand the concept of a gradient. And to understand the concept of a gradient, we need to understand the concept of first derivative. And to understand the concept of first derivative, we need to understand the concept of the rate of change. Simple, and it's really very simple. So let's start by explaining the concept of a change. We don't want to get too philosophical here, but the only constant in life is change. As we grow up, for example, our height increase, our physical appearance change, and this is just the purpose to explain there is a change with respect to a period of time. Some value change with respect to another value. Here, for example, the height or the physical development stage per time. How old are you? Another example for those people who like cars, especially these luxury cars. A guy bought a car, BMW car, with 5 miles on it, and then in 10 months, he put 50,000 miles on it. And look at the car. It's dirty, it's dented. That poor car has went through a lot of a change in these 10 months. So a lot of a change has happened in those 10 months. Now we will jump into the concept of the rate of change, and we will take an example let's say, for example, at Intel Corporation and the major corporations like Google, there's something called the grade level. And that states that an employee's performance should increase year over year. What do you mean by performance here? Let's say the number of tasks that you can accomplish per year or per day. So let's look at this example. An employee just joined, and his performance was 5 tasks per year. And they take this, like he started at 5 tasks and he ended the year, his performance was 5 tasks. And if you look 5 - 5 over 1 - 0, that's 0. His performance didn't change at all in the first year. Let's look at the second year, for example. The second year, he started at 5 tasks again because this is the performance, y equal 5. 5 - 5 over divided by 2 over 1, again his performance didn't change. So here the rate of change is 0. That's a poor performer guy. He's probably not gonna even make it to the layoff part. Gonna probably get fired. Just trying to make things intuitive here about the explanation of the rate of change. Now let's go to the rate of change as a linear equation, a line. The employee at the beginning, his performance was 0. He's just learning. At the end of the first year, his performance is 1. That's great. He made a change. So the rate of a change is 1. And even let's go to the second year, for example. He started with 1, and then it's now 2. Again, the rate of a change is 2. He has a constant rate of a change as he grows, as he spends more time in the company, and again operating within the same grade level, his performance is increasing. So that's good. That's what the company wants. Maybe they want more. Let's see another employee. His rate of change is quadratic. That means that's even better because that's the first year and the second year. You see he was over this period, he started with 1 and he ended with 4 because 2 squared is 4. 4 minus 1 is a 3 over 1. That's great. And then if you look at let's say, for example, his fourth year from 4 to 5, that's 9. That's amazing. Probably that guy's gonna get promoted. So this just to explain again, these slides, we wanna get very comfortable with the concept of the rate of a change. We have a quantity that it changes with respect to another quantity. In the example we presented for simplicity, it's for example productivity or performance with respect to time, or delta x over delta y. Now let's move to one of the most important concept is the instantaneous rate of a change. Suppose your manager asked you, hey, what is your rate of a change? What is your performance change in the current second? So usually when we talk about rate of a change or performance change, we talk about long period. As we see in the Intel example, we measure the performance for a whole year, or we can measure it for a whole month. But when we talk about the concept, how did your performance change in a second or a millisecond? That's a little bit awkward and a little bit weird. Like, what you gonna tell your manager? How you gonna measure your rate of change or your a change in productivity? So that is the concept of the instantaneous rate of a change and the first derivative. If you look here in the green box, this is where we take the rate of change for a period of 1, and then assume we actually reduce that period. Now it's from 2, for example, to 2.5, and then it's even more from 2 to 2.1. The idea is to keep shrinking this interval that we are measuring the rate of change against. And it turns out through something called limits, which is we assume that f of x plus h minus f of x over x as h approaches 0. That means this delta is not 0, but it is close to 0. So if we apply the function here, x squared, because it's a square function, we will get this nice algebraic formula. And then it seems that while with factoring, h can get eliminated and we will remain with 2x. So this is a very crucial concept. You can stare and look at these algebraic eliminations and how we factor things out after the presentation, but this is not very difficult. This should be very easy. And this is the idea of the instantaneous rate of change or the first derivative, is we need to know the instantaneous rate of change, like how much my productivity change from this second to the next nanosecond. this drives us to the concept of the first derivative. And thus, if you understand this, you're going to understand easily multivariate functions, partial derivatives, and that's important for the gradient descent too. Now, let's take this to something called minimum and maximum points in a function. For example, before we jump, look at this function here. This is called a minimum point, right? A function goes here. It's called this is the minimum point of the function. There is no value of y that is below this. This is a minimum point. And if you look at this nice function here in blue, this is a function that goes up and then goes down, goes up, goes down. So, sorry. Yeah, goes up, goes down. The green point here is called the local maxima, and the green point here is called the local minima. And there is an observation that's also very crucial to help us intuitively also understand how a loss function later is minimized, is that as we approach a global minima or a local minima, the rate of change or the instantaneous rate of change or the gradient or the value of the first derivative approaches zero. And see this dotted line right here? This dotted line represents the instantaneous rate of change. And you see as we approach this from either side, it approaches zero. Same thing for the local minima as well, because this is the line, this is y equals zero. And that's a very important concept as well when we trying to find the minimum of a function or the minimum point of a function. And that's again a very crucial concept and a very important concept in machine learning and also artificial intelligence. So let's talk about a little bit about a gradient descent or the whole family of algorithms of a gradient descent. So this is an x squared function, right? And the derivative of this squared function is 2x. If we are at point x equal 9, what is the instantaneous rate of change? It's 18. We're still far. Let's get a little bit closer to the minimum point at 1, for example. The derivative is 2x, so that gives us the instantaneous rate of change to 2. Now, of course, by just taking the derivative and doing the first derivative equals 0, we can right away know or figure out the minimum point of the function. But let's see, can we move x a little bit? So there is, if we update x with a value proportional to the gradient. So we have x equal 9. That means the gradient or the instantaneous rate of change will be high. If we update x to a value proportional to the gradient or the instantaneous rate of change, then we will get closer to the minimum point. So we're going to keep going down. I am x new. X old is my current value x, and this is my instantaneous rate of change multiplied by something called a learning rate. This is a way how we can move x. So the idea is we update our location or x with a value proportional to the gradient multiplied by something called a learning rate. And this shows how we can move gradually toward the minimum point. So let's look here, for example, the gradient descent, how we can update. At iteration 1, we start at x was 8.82 and see the gradient was 17.46 and the learning rate by the gradient is 0.18. After the update, we come toward 8.64 and see the gradient is getting less here. This shows that the gradient or the instantaneous rate of change again or the first derivative is getting less as we are approaching x equals 0, which in this diagram is the minimum value of the function. Now, let's talk about how do we build a model. So we explain the rate of change. We explain the first derivative. Let's talk how these all fit together to build a machine learning model. Now we have data, and this data actually we need to select the function that we are gonna choose to represent the data or the model. This can be neural networks, or this can be just a linear function where the number of rooms, for example, when we try to predict the price of a house, maybe the number of rooms is a very important factor in determining the price of a house or the number of bathrooms. So the machine learning will tell us what is the weight of the number of rooms in the value in the final price of the house. So, for example, it could be 100, and then maybe the number of bathrooms is not important, or it's very important, but the number of floors is less important. So it will be like -5 here or 0.1. So after we choose our model, right, we choose a model. We have the first part of the machine learning, building a machine learning model, is to choose a model, like an equation or a sort of a model that we will figure out its parameters. And then there is an error function, as we mentioned in the earlier, is that once we choose a model, we apply it to the data and we optimize the loss function. There is an error function, and that error function basically we get all the prediction minus the actual and takes called the sum of squares, or mean sum of squares is the prediction minus the actual value. We take the square of them and then we sum all these together. That's called the sum of squared residuals. So let's jump into it and see a real example of the house pricing. So here we have two houses, or how we go our data set. Here we are talking about a linear model, and we take the price of the house and we apply it to the model that we chose, and then we apply the loss function. So one bedroom, 1 by W1, two floors, 2 by W2, plus 1 by W3, plus W minus 1000 squared, and we sum all these together. Once we sum all these together, we get a final function in terms of W1, W2, W3, and W. And our goal is to find the value of these that gives us the minimum prediction error. So similar to what we have done in here, as you see in the previous slide, when we started at 9 and kept increasing the value of X until we reached the 0 or somehow close to the 0, we do similar thing here, but in multi-dimensions. So important concept. And this is the building block of the neural networks. And the neural networks is the building block of the generative AI. Suppose we need to be able to see how many research skills that you have. We need to be able to, maybe one means you are a great researcher. 0, you are absolutely not a good researcher at all. And the attributes we have is the number of hours, you work as a teaching assistant, the number of hours that you've worked as a research assistant, and the number of papers you've published, and the number of courses you've taken. Maybe the numbers of hours you were a teaching assistant were not that great in your research. Doesn't give you much experience. And research skill, it has a weight. So this weight could be 1 or 2 or whatever. So this is like a signal. And the number of research hours, it will definitely affect your research skills. The more number of hours you've worked as a research assistant, the more your research skills will be. So this will be of a higher weight in the activation function. And maybe the number of papers you've published, that might indicate also a greater research skills. Maybe the number of courses you've taken, not that much, it affects the knowledge, but the knowledge, again, maybe it's not that important in research. Research skills, you have to be able to read and learn on the spot. So if you look at these, we W1 by X1. X1 here is the number of hours of teach. So basically, this is a weight, the weight of the specific attribute or feature of how it affects the research skills. We take all of those and we produce value. We produce a final value. And the purpose of the activation function is to produce a value between 0 and 1. This is just an example of one activation function. We're being very simple here. The more the value is, the higher the value will approach 1, and the less the value is, the closer the value will approach to 0. And then this is again indicates your research skills. So I'm just for explanation purposes, this is not the only activation. There are so many activation functions. Some activation functions produces values between -1 and 1. And let me skip a slide. Yes, okay. Now let's go to the activation function, introduction to neural networks. Basically, the neural network is just a combination of activation functions. I am trying to predict something final, like the number of patents you're gonna produce by starting from a basic set of attributes about you. Like, for example, the number of hours you have taught as a teaching assistant will affect your maybe knowledge, breadth of knowledge, or and the number of courses you've taken will affect in somehow your breadth of knowledge or depth of knowledge. And each of these, as we've seen here, each of these has a specific weight. So the number of hours you have teach will have a different weight on research skills than the weight it has on the breadth of knowledge and the depth of knowledge. And again, this attribute, that's why we call it feature transformation. Now, the feature that we started with are transformed to another set of features. Okay, let's do the same thing again. Well, maybe presentation skills will be important in grant writing, for example, and the depth of knowledge will affect creative thinking. Each of these, again, transformed features will affect these ones in green in a different way. Research skills might have a higher weight on you working independently. So you might give it a value of 100 or 200 or 300. And again, all of these, we combine them and see how each of them will affect the number of patents that you're going to publish. So the machine learning process, the purpose of the machine learning process is to determine the weight of these arrows over here. Once we know the weight of each of those, we have our nice, beautiful model that can help us build predictions. So I think we can move to the next slide about how they did come out with this. So actually, this is a model, and this is the neural networks model, and actually works pretty well. And that's even the generative AI is based on that. Now, how did scientists come up with this nice, beautiful, colorful model that we've seen? So actually, I have to mention one thing before I move to the next slide is when we build neural network models, we necessarily do not understand what these inner nodes are. It's just this is just for us to help us understand how it works and what is the feature transformation. Basically, a specific feature affects a feature in a different way than it affects another feature. So where did it really start? How did it really start? It started from, yeah, again, as you mentioned, the first slide is always scientists try to understand how the brain works. And when they studied the brain, they realized there is a bunch of neurons connected to other neurons. And each neuron sends electric signals to other neurons. And the values of the electric signal varies depending on the strength of the message. So once they've studied this, they try to imitate that, and create neural networks, and it ended there. And I mean, like the reliance on that, that's where they got it from the brain, and then it took on a world of its own, generative AI and a lot of stuff, and so many advancements and appeared from there. Uh, Now let's see some suggested material. When I started reading about machine learning, I studied these resources. I highly recommend Highlights of Calculus by Professor Gilbert Strang. He will explain nicely the first like the derivation, the integration, and all of the math necessary for you to understand these things. And he's a very good professor. He simplifies things really very well. So the input to your learning process will be a very good quality data. You will be able to build very great models by watching these lectures. And I like the machine learning regression on Coursera by Professor Emily Fox and Professor Carlos Guistrin. And there is also an excellent series of lectures by Professor Tariq Abu Mustafa from Caltech. We've watched